Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we consider our corollary and some theorems on group. Statement of corollary is a homomorphism F from the group G onto the group G dash is an isomorphism if and only if kernel of F equal to singleton E, where E is the identity element of group G. This statement can be asked for objective as a homomorphism F from the group G onto the group G dash is an isomorphism if and only if dash dash kernel of F equal to singleton E, where E is the identity element of group G. Now we consider one theorem. Statement of this theorem is, let G be a group and H be a normal subgroup of group G. Then G by H is a homomorphic image of G with H is at its kernel. Let us consider the proof of this theorem. Let G be a group and H be a normal subgroup of group G. Then G by H equal to set H plus A such that A belongs to G bracket complete is a quotient group. We have to show that G by H is a homomorphic image of G. For this, let us define a mapping F from G to G by H by f of A equal to HA for all A belongs to G. First criteria is F is well defined. To prove this, let x equal to y. Then x equal to y implies hx equal to hy, and which implies fx equal to fy. Therefore, f is well defined. Now we can prove f is a homomorphism. So, let a comma b belongs to G. Then f of ab equal to h of ab, and which is equal to ha into hb, since f is an homomorphism, which is equal to f of ha means fa, hb means f of a, which is equal to f of a into f of b. That is f of ab equal to f of a into f of b for all a comma b belongs to G. Therefore, f is a homomorphism. Now we prove that f is onto. To prove this, let ha belongs to G by h. Then ha belongs to G by h implies a belongs to G. Thus, for all ha belongs to G by h, there exists a belongs to G such that fa equal to ha. Hence, f of a is onto. Thus, f is homomorphism of G onto G by H. Therefore, G by H is a homomorphic image of group G. Now we prove that kernel of f equal to H. Kernel of f equal to set of all A belongs to G such that f of A equal to H, where H is identity element of G by H. Thus, A belongs to kernel of f is implies and implied by f of A equal to identity element of G by H, and which implies and implied by f of A equal to H, and which implies and implied by h of A equal to H. Both way implication implies A belongs to H. Therefore, finally, we get A belongs to H. Therefore, A belongs to kernel F if and only A belongs to H. Thus, kernel of F equal to, thus we get kernel of F equal to H. Now we consider one fundamental theorem of group homomorphism, which is theorem number 9. Statement of this theorem is if G is from if f is from G to G dash is an onto homomorphism with kernel K equal to kernel of f, then G by K is isomorphic with G dash. That is, this can be written in another formats. This can be written in another formats. Every homomorphic image G dash of a group G is isomorphic to a quotient group of G dash. That is every homomorphic image G dash of a group G is dash dash or is isomorphic to a dash dash quotient group of G. In this way, objective questions can be asked. Let us consider the proof of this theorem. Let f is from G to G dash be an onto homomorphism with K equal to kernel of f. But we know that K is normal subgroup of group G. And we know that if K is normal subgroup of group G, then G by K is a quotient group by definition of quotient group. Here we have to prove that G by K is isomorphic with G dash. To prove that G by K is isomorphic with G dash, we define a function phi from G by K to G dash by phi of Ka equal to f of A for all A belongs to G. We shall prove that phi is an isomorphism. That means we have defined here to prove that G by K is isomorphic with G dash. We defined a function phi from G by K to G dash by phi of Ka equal to f of A for all A belongs to G. Here we prove that phi is an isomorphism. Isomorphism means homomorphism. Function is 1, 1 and 1, 2. First we shall prove that phi is well defined. So let Ka equal to Kb, where A comma B belongs to G. Then Ka equal to Kb implies AB inverse belongs to K, where K equal to kernel of F. This implies Ka equal to Kb. This implies f of AB inverse equal to E dash. And this implies f of A into f of B inverse equal to E dash, since f is an homomorphism. And this implies f of A into bracket f of B bracket inverse equal to E dash by theorem number 1. And this implies f of A equal to f of B. This term is taken on right hand side, so we get f of A equal to f of B. But f of A means phi of K. Thus we get phi of K equal to phi of Kb. That means Ka equal to Kb implies phi of Ka equal to phi of Kb. Thus we have proved that function phi is the function phi is well defined. Now we consider second proof. phi is 1 1. That means we have to prove that phi is 1 1. To prove that phi is 1 1, let phi of Ka equal to phi of Kb. Then phi of Ka equal to phi of Kb implies f of A equal to f of B. And this implies f of A into bracket f of B bracket inverse equal to E dash, since f is an homomorphism. And this implies f of A into f of B inverse equal to E dash by theorem number 1. And this implies f of AB inverse equal to E dash. And this implies AB inverse belongs to K. And this implies Ka equal to Kb by property of cosets. Hey, that is phi of Ka equal to phi of Kb implies Ka equal to Kb. Hence, function phi is 1 1. Now we consider third part, phi is onto. That means we have to prove that phi is onto. To prove this, let y belongs to g dash. Since f is onto function, there exists a belongs to g such that y equal to fx. Corresponding to this y equal to f of a. Corresponding to this f of a belongs to g dash. There is a coset Ka in g by k such that phi of Ka equal to f of a. Hence phi is onto. Now we consider finally isomorphism. Let Ka comma Kb belongs to g by k, where a comma b belongs to g. Consider phi of Ka dot Kb bracket complete, which is equal to phi of k into ab bracket complete, which is equal to f of ab, and which is equal to f of a into f of b. But f of a means phi of k, f of b means phi of kb. That means here we consider Ka dot kb belongs to g by k, where a comma b belongs to g. And by considering phi of Ka into kb, we get this is equal to phi of kab. And phi of kab equal to f of ab. And f of ab equal to f of a dot f of b. But f of a means phi of k, f of b means phi of kb. So that phi of ka into kb equal to phi of ka into phi of kb. Thus, phi of ka into kb equal to phi of ka into phi of kb, where a comma b belongs to g. Hence, phi is an isomorphism. Since we have proved that phi is well defined, phi is function 1 1, phi is onto, and finally we prove that phi of ka into kb equal to phi of ka into phi of kb, where a comma b belongs to g. That means phi satisfies all the properties of isomorphism. Hence, phi is an isomorphism. Thus, here g by k is isomorphic to g dash. That means here we get g by k is isomorphic to the group g dash. That is, g by k is isomorphic with g dash in notation. Thus, we have proved that if f is from g to g dash is an onto homomorphism with kernel f equal to k, then g by k is isomorphic with g dash. That means objective question can be asked as, if f is from g to g dash is an onto homomorphism with k equal to kernel f, then dash dash g by k is isomorphic with g dash. Or this statement can be written in another format, every isomorphic image G dash of a group G is isomorphic to a dash dash, that is quotient group of G. Thus we have proved the theorem. For proof, we consider function f with kernel f, then we defined function phi from g by k to g dash, and we prove that phi is an isomorphism. Thus we have proved that g by k is isomorphic with g dash, where f is from g to g dash is homomorphism with kernel f. Thank you.